Hello and good afternoon, everybody. So, here today I will introduce you to the phase petrology part 2, and there we have now, or I have prepared for you now some exercises. So, we will go now in detail through the exercises. Some of the exercises you can maybe already solve it, and the other exercises we will then do more or less together when you are back at the university on the 4th of May. So we can do every day an exercise, or we can start with the exercise, and you can then finishing the exercise at home, and I will give you marks for every exercise. You know, I have now to collect as much as assessments as possible so that I'm getting a good overview for the final marks then for you. So then for the remaining classes this week, we will talk a little bit about the Big Bang and our solar system. Yeah, that is not part of the examination, but I think it's a very good thing that that you have heard about it. Yeah, and today I'm making this introduction into the exercises, because then you can already start to do some of the exercises and think about. So for the classes next week, I mean, you have by now all the necessary videos that you can or that you are able to answer all the questions. You will get next week also another assessment, or we can write it next week or in 2 weeks time like a test. Yeah, we can also do this. And then we have also to go to the field trip, and then we are through with this class. Okay, then let us just continue. So here I have then some questions prepared for you. Question number 1, that is thermodynamics 1, qualitative phase diagram of water. We have done the qualitative phase diagram of water. So and now in this exercise, you should describe and draw a schematic PT diagram of the different stability fields of the system H2O. Please consider only one solid phase. Yeah. So and then you should also add the changes in entropy. I mean, which phase has the highest entropy, which phase has the lowest entropy. And you should also write down which phase has the lowest volume and which phase has the biggest volume. Yeah, that is not that difficult, but just for understanding. So then thermodynamics 2, there you should draw the qualitative phase diagram of the alumosilicates, and you know the 3 alumosilicates, that is kyanite, sillimanite and andalusite. All 3 of them have the same mineral chemical formula, which is Al2SiO5. So that means these are polymorph minerals. So, and for a qualitative estimation about the location of the 3 univariant reaction curves in equilibrium following in the PT space, there we need then following informations. So I mean, the entropy for sillimanite is sillimanite has the highest entropy. Then andalusite has an entropy, a medium entropy, and kyanite has the lowest entropy. Yeah, and we discussed by now the relationship, or how the entropy is connected to the volume, and how the entropy is connected to the temperature. So, and then we have the volume from andalusite is the smallest one, then the volume of silimanite is the medium one, and the volume of kyanite, now the volume of andalusite has the biggest volume, then we have silimanite, and kyanite has the smallest volume, yeah? So, and you need this information that you can construct the qualitative phase diagram of the alumosilicates. So, and I mean, I uploaded to you, or I gave you these two books, yeah? And if you are going through this book, that is this one from Chatterjee, and the other one is from Roger Paul. The other one, the book from Chatterjee is called Mineralogical Thermodynamics, and the book from Roger Paul is called petrological thermodynamics or something like this, and there you will find a lot of answers to the questions which I have written there. So then we coming to the next one, and that is now a little bit a complicated one, but I'm sure you will be able to manage it using the information what I have given you here. So you should then thermodynamics 3, that is questions belonging to thermodynamic 1 is very easy. Questions belonging to thermodynamic 2 is medium. Questions belonging to thermodynamics 3 is difficult. So, and there we have now, you should not make a qualitative phase diagram of the alumosilicates like before. Here you should making a quantitative phase diagram of the 3 alumosilicates. And therefore I have found in the literature, I got the following thermodynamic data for the kyanite, for the andalusite, and the silimanite. So then we have the value for the Gibbs free energy at standard conditions for the kyanite, the value of the Gibbs free energy at standard conditions for the andalusite, and the same for the silimanite. I have written down here the values for the entropy at standard conditions for the kyanite, the andalusite, and the silimanite. So, and then I have also written down the volume at standard conditions for kyanite, andalusite, and silimanite. So now what should we do, or what should you do? Calculate the conditions at equilibrium of all 3 reactions, which are possible between all the 3 modifications. Construct a PT diagram for the stability fields of all 3 minerals, and calculate the PT conditions at the triple point. For the solution of this exercise, you can assume that the entropies as well as the voluminas of the 3 phases are pressure and temperature dependent. Start with the following equation. If you are going through the outline of phase petrology 1, you know, which I have just given or recorded it last week, then you should be able to do these calculations, and you must know, or you should have always in mind, that these are all linear equations, yeah, and linear equations, you know, from math in school, that is f of x is mx plus b, yeah, these are all, and then you have just to fill in these values. Then we have here again an easy calculation. We have a zinc sulfate at standard condition. Zinc sulfate exists in 2 mineralogical modifications, that is the sphalerite and the wurtzite. The sphalerite is cubic and the wurtzite is hexagonal. Following values have been found in a table. So here we have the enthalpy values at standard conditions for the sphalerite and the wurtzite, and we have the entropy values at standard conditions for the sphalerite and the wurtzite. So, and now the questions to be answered is, which of the both modification is stable at standard conditions? So then we have a little bit a more difficult question, thermodynamics 2, gold and water. So the situation is we put a hot piece of gold with the mass of 200 grams and the temperature of 120 degrees Celsius. We have thrown this hot piece of gold in a 10-degree cold water bath with a mass of 25 grams. So that should not be 25 degrees Celsius, that should be 25 grams. So to which degree will the entropy of A, the metal B, and water C, or to which degree will the entropy of the metal, the water and C, the whole system change till equilibrium is reached? Assume that the whole process will take place in a closed system. And I have again to mention the mass of the water basin is 25 grams and not 25 degrees Celsius. So, and that is a CP function which you need for this calculation. You don't know by now the function, but you can study this in the textbook Mineralogical Thermodynamics. Then we have a more difficult question, thermodynamics 3. We have the solid-solid reaction of quartz plus grossular. We'll go for 2 wollastonite plus anorthite. Following reaction is given, we have quartz plus grossular, and then we will form 2 wollastonite plus anorthite. Below you have the mineral chemical formulas. For the given reaction at 1, 2 and 3 kilobar within a temperature interval of 400 to 800 degrees Celsius, the chip's reaction energies has been calculated. So, and that is in a table, in the next table. So then question number A, express delta G at the pressure of 1, 2 and 3 kilobars as a function of the temperature in degrees Celsius. That should be temperature and not temperature. Explain the consequences from the resulting function regarding delta H, delta S, and delta Cp of the reaction. So then you should draw a PT diagram at equilibrium for the given function, not function with correct parameters. And then you should answer, is the resulting reaction a geological thermometer or barometer? So, and here we have the table, and if you have followed the class that the reaction goes always there where the chip's free energy becomes zero, negative, then it should be now an easy thing to draw the 3 reaction curves, at 1 kilobar, the next one at 2 kilobar, and the next one at 3 kilobars. Then you can put or it is up to you, you can put on the x-axis the temperature and on the y-axis the values for the chip's free energy. So, and that is the table for that. And you know, if you have a steep reaction curve, then it is a good thermometer, and if you have a flat reaction curve, then it is a good barometer. Then we have two more complicated questions. We have thermodynamics 3, plot N-statite, which is MgSiO3, forsterite, which is Mg2SiO4, and kyanite, which is AlSiO5, spinel, which is MgAl2O4, and pyrope, which is Mg3Al2Si3O12, on a MgOSiO2Al2O3 mole fraction triangular diagram. Please note that the ratio between Al2O3 and MgO and SiO2 is 2 to 1. Because when we are talking about aluminium oxide, we are dealing with Al2, and Mg and SiO is just 1 mole. Therefore, I mean 2 to 1. And you should just put in your reaction triangle the relationship between Al, magnesium, and silica. So then you can plot all these minerals inside a triangle. You should know by now how this works, yeah? So, and then you should write all the reaction between the phases in question 1 and balance them. Use the triangle and the cross reaction method. So, and that you should know by now as well. So then B, construct the Schreinemakers diagram in the binary system of question 1 between the end members periclase and quartz. C, construct the Schreinemakers diagram in the ternary system of question 1 with SiO2 in excess. And you will find for that also some examples in this book which I sent to you, which is entitled Petrological Thermodynamics. This is this book from Roger Paul. So, and here we have the same situation but other minerals. You should plot grossular, which is Ca3Al3Si3O12, and quartz, which is Si2, and zoisite, which is Ca2Al3Si3O12OH, anortite, which is CaAlSi2O8, and silibanite, which is Al2SiO5, on a CaOSiO2 Al2O3 mole fraction triangular diagram. H2O has to be treated in excess. So, and then you should write all the reactions between the phases in question 2 and balance them. Use the triangle and the cross method, and then you should construct the Schreinemakers diagram for the ternary system, and then you can just do, or we are doing this just when you are back next week. So these are then the last practical exercises besides some microscopic work which we will do when you are back, but the time is very short. Okay, bye.